Small sample hypothesis. Example 5a. In a sample of n equal 4 tosses of a coin, the proportion of heads, p hat, 3 out of 4. As a decimal, 3 divided by 4 is 0.75. If the coin is evenly weighted or fair, the proportion of heads in the long run should be 1 over 2. You have one chance out of 2 of being a head, one chance out of 2 of being a tail. As a decimal, that'd be 0.5. Okay. And the proportion of tails in the long run would be 1 minus 0.5, which is also 0.5. And we want to test the following hypotheses at the alpha equal 0.05 level of significance. P equals 0.5. If the coin is evenly weighted, we expect heads to turn up half the time. If the coin is not evenly weighted, it could be either less than half the time or more than half the time. So this is a two-sided test. The coin would be unevenly weighted if there's either more heads than tails or fewer heads than tails. Okay, so we want to check whether n times p0 is at least 5. So our sample size is 4. P0 is 0.5. 4 times 0.5 is 2. And it's not greater than or equal to 5. Okay. And then we want to check whether n times q. Actually, we don't even need to bother to check with n times q. We already have a no here, but we'll also do it here. It's 4 times 0.5 again. It's 2 greater than or equal to 5, and that's a no. So that means we can't use the z-table. We'll have to compute the exact probabilities. And we'll usually be doing that with a tree diagram. The full tree diagram would have 16 paths. But we really only need to show the paths for which either the proportion of heads is greater than or equal to 3/4, or the proportion of tails is greater than or equal to 3/4. So we want to include both extremes because of this is a two-sided test. We have a not equal to symbol in HA or H1. So H1 here. And because the coin would not be evenly weighted if in the long run it turned up either more heads or fewer heads than tails. Okay, so we'll make a tree diagram, and again, we just for convenience we'll only include the paths with either at least 3 heads or at least 3 tails. The first path here is all heads. It's head, 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 and head, 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 head. So the probabilities are going to be 0.5 times 0.5 times 0.5 times 0.5. It's 0.0625. Okay, and these probabilities are all going to be the same. So the next path ends here with a tail. So we had 3 heads followed by a tail. It's going to be the same probabilities. It's 0.5 times 0.5 times 0.5. So these are all going to be the probability 0.0625. The next path we have 2 heads followed by tail followed by head. And then we have head tail followed by 2 heads. .0625. A head followed by 3 tails. .0625. Tail followed by 3 heads. Tail followed by a head and 2 tails. two tails followed by head followed by tail. Three tails followed by head, and the bottom one's going to be four tails. Okay, so again, I didn't do the full tree here. I just wanted the paths that had either at least three heads or at least three tails. Okay, so there's 10 paths altogether. 1, 2, 3, 4, 5, 6, 9, 10, and these probabilities are all the same. So the total here, 10 times 0.0625, 0.625, and that's our p-value. Our p-value is 0.625. It's more than our significance level, 0.05, so that means we fail to reject H0. Sample does not provide enough evidence to say the coin is unevenly weighted. Okay. We could also do this with a tree with a chart instead of a tree diagram. We just in the chart we just list the paths with at least three heads or at least three tails, and if you're doing this in MyLab, actually the MyLab doesn't have a capability to make tree diagrams, so but they do have capability to make tables, so you're likely to see a table instead of a tree diagram here. And there's one row of the table that's missing here, and we have to figure out the missing row. So let's see, we have a tail in the fourth position, the third position, the second position, the first position, with three heads. And let's see, let's look at three tails followed by head. Let's see, we have a head and three tails here. And then that's in the first position. A head and three tails in the second position. A head and three tails in the third position. So the only thing we don't have here is three tails followed by a head. Tail, 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 head. So if you're doing it in MyLab, Pearson MyLab, you need to fill this in exactly the way that this exact same format as they're using for those other paths. So you're going to write out tail, capital T, small letter A-I-L, slash, and tail again, capital T, small A-I-L, slash, tail, capital T, A-I-L, slash, and then capital H for head, H-E-A-D. And the probabilities are going to be the same as for the other ones. It's going to be 0.5 times 0.5 times 0.5 times 0.5. 0.0625, and the grand total p-value of 0.625. So you could use either a tree diagram or the table, but if you're doing it in Pearson MyLab, they only do it with tables there. Okay, so just sort of the terminology of hypothesis testing. Either H0 is true or H1 is true. Either we don't reject H0 or we reject H0. So there's four possible outcomes from hypothesis testing. H0 could be true and we don't reject H0. H0 could be true and we reject H0. That would be a type 1 error. H1 could be true and we don't reject H0. That's a type 2 error. H1 could be true and we reject H0. 1 minus alpha is our desired level of confidence. That's the probability we don't reject H naught if H naught is true. Alpha, the Greek letter alpha, desired level of significance. I like to call it the desired level of doubt. It's also the probability of a type 1 error. That's listed here as the probability of rejecting H naught if H naught is true. P-value would be the actual level of doubt. And Greek letter beta represents the probability of a type 2 error. We need to make some additional assumptions in order to compute the probability of a type 2 error, so that's usually not computed. We won't be computing the probability of a type 2 error. You might be doing that if you take Math 251. You might see that there. 1 minus beta is called the power of the test. Usually we'll require at least moderate evidence, which would correspond to a p-value of less than or equal to 0.05 in order to reject H naught. We never accept H naught technically, actually. You'll see some language of accepting H naught even in my lab or WebAssign, even in textbooks, but technically we never accept H naught. Either we reject H naught or we don't know. And in this particular example, because we failed to reject H naught, we take a chance of making a type 2 error. So either way, you always take a chance of making some type of error. If you reject H naught, you take a chance of making a type 1 error. If you don't reject H naught, you take a chance of making a type 2 error. The way to reduce the chances of either type of error are to increase the sample size, but the drawback there is that the larger samples can be expensive. So example 5b, if we redo example 5a, but in this case the proportion of heads is 4 out of 4, we can use the same tree, but now we only need the two paths instead of 10 paths. So we just need the 2 paths where either we have 4 heads or 4 tails. So we want to test either extreme. It's still not enough evidence to reject H naught. If we have these 2 paths, we get 0.0625 plus 0.0625, which is 0.125. So it's still not enough evidence to reject H naught. Example 5c, find the p-value of the proportion heads is 6 out of 6. So instead of 4 heads in a row, we're going to have 6 heads in a row. And also we'll have 6 tails in a row. So so the 2 paths where we have at least 6 heads or at least 6 tails will have 6 heads, and this probability is 0.5 to the 6th power, 0.5 times 0.5 times 0.5, etc. So 0.5 to the 6th power, 0.015 something, 625. And the probability of 6 tails would be the same. And if we add these, we get 0.31 something. 0.03125. So in this case, if you had 6 heads in a row, that would be enough evidence to reject H naught, because our p-value of 0.03 is less than 0.05, so that would be enough evidence to reject H naught. Okay. And that concludes this presentation.